We will call now for the stage Nurit Shtober for the presentation fire-induced rock flakes as long-term containers for trapped ash. Please, Nurit.
Hello, everybody, and thank you for coming to my presentation. My name is Nurit Shtober, and I would like to present you our research entitled Fire-Induced Rock Flakes as Long-Term Containers for Trapped Ash, which together with my colleagues Anna Brook, Daniela Koppel, Lea Wittenberg from the University of Haifa, and Dar Roberts from the University of Santa Barbara. My interest in fire-induced rock flakes started after a major forest fire that occurred in Mount Carmel in 2010. During that fire, or after that fire, we noticed massive destruction of the rocks exposed and severe acceleration of these rock outcrops, which probably occurred due to the high temperatures and the sudden heat shock that affected the rocks by cracking, spalling, and flaking. The effects of the fire depend to a large extent on rock physical properties and vary with lithology. We noticed that the chalks, which were covered by Nari crusts or by calcrete crusts, they were the most affected rocks. They were decayed to up to a depth of 20 centimeters and on average to a depth of 3 centimeters. They were detached during and after the fire, and in most cases, in all cases, the fire severity was defined as high. And it occurred at high temperatures. We don't know yet what was the temperature, but we know it was high or defined as and rated as 3. The spalling process occurred both during the fire and during the subsequent cooling of the rocks. As you can see, scorched surfaces at several depths of the rock surface. One more image of these flakes and spalls. And to summarize the introduction, the pre-fire stage, during the pre-fire stage, we saw the slopes that were covered by vegetation, soils, and rock outcrops. After the fire, the boulders were spalled, the trees or the vegetation was burnt, and a thick layer of burnt organic material and the ash covered the soil. In the next years, the spalls and flakes were transported down slopes. More and more flakes covered the soil, and less flakes remained on the surface of the rocks. In the third year after the fire, just a few spalls were still visible on the large boulders, but most of them were transported downslope. We summarized this observation in a paper published last year in the International Journal of Wildland Fires, and kept an eye on those flakes and what happened to them. In the next years, we noticed that when we manually removed flakes, we could find ash under those flakes. The rock outcrop was burned in 2010. The picture was taken in 2016. Six years after the fire, we manually removed that flake and we found ash. In the soil, we couldn't see the ash. Here, in the soil, we couldn't see the ash. The ash is not visible in the soil, but it was present under the flakes. And we removed one by one, and it was there. On the other hand, when in recently burned regions, ash was present on soil surfaces, but was unnoticeable beneath the rock flakes. The flakes served an isolating shield to the previously trapped sediment and organic material. This observation triggered several questions, such what is the time span for ash particles to be preserved in the traps? Or when does the ash penetrate under the flakes, during the fire or later on, subsequently? What are the transport mechanisms and what role does the ash play in the flake detachment? I'm not sure that I'll be able to answer all these questions. However, the aims of the study, the present study, are to recognize the evidences of ash trapped in the slope system, to learn what is the time period that ash can be preserved in these traps, and to assess the importance of the trapped ash in slope evolution processes. The study area is the Mediterranean area of Israel. In Mount Carmel, which is located in the northern part of Israel, and the Judean hills, which are located in the central part of Israel, the bedrock is similar, chalk and limestone, mostly covered by nari, or calcrete crusts. The climate is Mediterranean, ranging from 500 to 700 millimeters in the upper parts of the mountain. Soils are Mediterranean, brown Ranzina or Terra Rossa, and vegetation was Mediterranean evergreen sclerophyll forests. So what did we do? The sampling method, or the sediments were collected between November 2015 and January 2016, based on the time span from the last fire. We picked up 4 previously fires in 2015, 2010, 2005, 1989, which means 6 months before our samplings, 6 years before, 11 years before, and 27 years before our samplings, and of course a control site. So we chose 4 burning sites and 1 control site. In each burned site, we picked up 10 outcrops. An outcrops are rock outcrops. A rock outcrop will be picked up 10 outcrops, and we measured 3 spots for each outcrop. Above the exposed rock, below the exposed rock, and on the exposed rock, but under the flakes. We call them A, above, B, below, and X under the flakes, and I will refer them in my presentation. And we measured ash-related minerals. We measured 9 features that were detected. 6 of them were detected by drift spectroscopy across mid-infrared spectral region. We measured hydroxylapatite. We measured smectite montmorillonite, kaolinite, black carbon or charcoal, and organic carbon, organic material, and aliphatic to hydroxyl ratio. We calculated the aliphatic to hydroxyl ratio. We also measured 3 physical parameters: pH, electric conductivity, and soil color using Munsell. The statistical analysis, I won't talk too much about the statistical analysis here. ANOVA, PCA, and silhouette analysis on key-means clustering. Now, in the following graphs, we have on the x-axis, we have the years, 1980, starting with 1989, and 2005, 2010, 2015, AXB, AXB, and so on, and the control. These 4 parameters, hydroxylapatite, charcoal, and the organic material, either as organic matter or at this ratio, were the best parameters that we measured. We can clearly see here that in 89, 2005, 2010, 2015, we found the traces of ash under the slopes as well as in the soil. However, under the flakes in 2005 and 2010, the signal was stronger, implying on the larger amount of ash that was trapped under these flakes. In the control area, we didn't find anything. We didn't find hydroxylapatite, as we didn't find charcoal in the control area. Now, as for 2015, under the flakes, the amount of the ash trapped under the flakes was smaller, since the flakes served as shields and protected the ash trapped, or the sediment trapped underneath. The organic material, we see the opposite, but it's the same. It's the same picture. We see a larger amount of organic material in 89, and in the control area about 17–18% of organic material, and then a less amount in 2005, 2010, and 2015. The clay materials were normally, or were in a normal amount on the slope, and it seems that the montmorillonite was not affected by the fires. The kaolinite, we saw a slightly increase in the kaolinite. pH was alkaline, as the substrate is carbonate, but the differences were limited and insignificant, as well as with the EC, with the electric conductivity, although in 2015 we saw a small increase in the values. As for the color, we found 3 clear clusters, but the color determination using the Munsell chart, we couldn't distinguish between the very dark shades, except of 2015. In 2015, we could clearly distinguish between the material under the flakes and in the soil. Since under the flakes material was not burned, the flakes served as an isolating shield for the previously trapped material. So wind action, gravitational movements, and biological processes were not sufficient to transport and to introduce this particle under the flakes in just half a year and without rainfall. As for the conclusions, rock flakes commonly serve as shelters for sediments and organic matter which are stored underneath. Severe wildfires accelerate in situ rock spalling and flakes formation, and consequently post-fire penetration of charcoal and ash particles. Fire-induced rock flakes serve as sediment containers for at least 20 to 30 years after the fire, and possibly longer, trapping and storing fine particles and leaving them in the slope system. And among the 9 parameters that we studied, hydroxylapatite, charcoal particles, and organic matter content proved to be the most sensitive indicators for the past fire events. The clay composition, smectite, montmorillonite along the slopes and beneath the flakes implies on the same clay origin for both locations. And in the Mediterranean flakes, apparently, the time required for ash to accumulate under the rocks is longer than a year, or at least one rainy season. I would like to thank once again to the United States-Israel Binational Science Foundation that supported our study, and special thanks to Naama Tesler and Hania Masha, who helped us in the field. And thank you very much again.
Thank you, Nurit. There is time for one question, please. No? Hi, okay. Stefan.
Well, thanks for a fascinating presentation. Just a quick question. Do you have any sense of how much ash material is stored underneath those flakes compared to the total amount of ash that would have been generated in a fire?
I cannot give a number, but very small amount. It could be grams or even less of grams. I know that, I remember the fire in 2010, and there were huge amounts of ash, but then this is what you saw here in terms of grams or even less.
Thank you.
After 6 years. In other cases, I don't know.
Okay, thank you.
Is another question?